All right, guys, I'm coming around to C unit, chapter 5. Hold it up for me because I'm not going to be there for more than a second. Hold up. I'm looking for which one's being held on. I said thumbs up, my bad. I got Yeah, all right, I'm going to scroll down because you should have had notes on number 1. You have 2 names, right? All right, I'm going to scroll down a little bit to question 3. Try to choose something different than your partner nearby. I know a bunch of you guys were absent on Friday, maybe 4 or 5 of us. Make sure your stuff gets in the box. Who's Cody's partner and Jesus' partner? Buddies, yeah, grab a buddy. Shaden, who are you? Simon, thank you. Let me take attendance. All right, so question 2 really sets you up for success for question 1. So let's go through question 1 versus question 2. All right, so step 1, what do you have to do? Take the percentage as its decimal form. So there's a percentage here and a percentage here. Okay, so for chromium 51, chromium 52. All right, so what is the decimal format of this percent for chromium 51? Everybody? 0.018. Good. So you're backing decimal up 1, 2, which is dividing by 100. This one? 0.982. Okay. And then what am I doing with both these percentages now? By their actual mass. So it's not like an average mass at this point, it's an actual mass. And since the chromium 51 gives us a really specific mass and chromium 52 gives us a really specific mass, we're going to use the most specific value we have, which we can. And you guys should have calculators at this point. If you don't already, grab one. It's kind of one of those new habits you're trying to start to form. for this class. All right, so my people who've already calculated, and let me get, sorry, I gotta get names because usually I can't hear like 14 responses. Lindsay, do you have, say again? Oh, you haven't calculated yet, okay. Kush, do you have me? All right, raise your hand, calculation. Yes, right here, Ainsley.
Like the total answer.
Give me this first answer.
51.28495.
28495. Okay, and then bottom answer, raise your hand if you got this one.
Oh wait, that was the bottom.
That was the other one. 51.28495. Okay, and then I figured that. I was thinking that was a little large for this 0.018. All right, got me? Go for it, Michaela.
0.917.
Okay, and then once we get these values, what do we do, guys? Add them. What do we do after that? Great job. Nothing. Okay, just look at sig figs. Don't do any division at the end. Just making sure we're not doing any other averages. So when we add this up, what do we get? 52 point what? 52.2028. Okay, so we got a long chain of numbers here, but it looks like we're probably going to have, since in the end, like I know we're adding, and these sig figs will differ when we multiply. The percentages themselves are not measurements. These numbers here are the measurements. So notice there's 3 places after decimal, 3 places after the decimal. I need 3 places after the decimal. So round that, what do you get? 52.203 AMU, atomic mass unit. That would be the most appropriate unit for mass. Everybody find chromium on their periodic table? Have the periodic table out for me, so at least maybe one of your partners can pull it out so you guys can reference those. Which location in the is it on the periodic table? Which location?
Oh,
right there, so like kind of smack dab in the middle of the transition metals, but it's towards the top. And what is its average mass? 52.00, right? So that periodic table has a slightly different average than what we have calculated, but we're pretty darn close. So that's how you can kind of check your work on a test-like situation, so you're not too far off. Okay, for the last one, let's go. I need a symbol, like what element we're talking about, and then one of the isotopic notations. Alicia, what you got? Nitrogen, okay. What do you know about nitrogen? Where do I put that? The bottom. Good. 7 is the atomic number, also known as the Z number. Okay, keep going. Okay, 15 is one option. If you look on the periodic table, everybody look at the periodic table. What is the average atomic mass of nitrogen? 14, but that's just one isotope of nitrogen. There is one that weighs 14. There's one that weighs 15. There's one that weighs 13. So that's a valid option. And then what if I told you I wanted you to make it a charged ion of a -3 charge? Where would you put that? Top right. Good. So this is one way that's like super thorough, very informative. All right, tell the person next to you how you'd write this with the mass notation. All right, Jake, you had it spot on. Nitrogen.
yeah, dash mass.
What's the mass here?
15.
15. And since it's a charged particle, it's an ion, I do need to put that here just because I've included it on the first one. Something like that. So we went with the isotope 15. The averages, that's what we just talked about. The average is 14, but there's other isotopes in the world that nitrogen can exist as. Okay? All right, so that's a quick review from Thursday and Friday. Today we're talking about light. Okay? So, chapter 5. I saw a couple questions about number 9. So the idea is that we now have, sorry, okay. So we have a general idea about the atom, right? Who's the very first person to kind of think about the atom? Democritus and Aristotle. Then you came to next. Okay, that was one scientist that you know. Yes, look back at your notes if you don't remember. So Dalton's atomic theory. So we just started developing more ideas. J.J. Thomson. What was his specialty? What did he go for? Say again? So what subatomic particle did he find in the end? The electron, right? He developed the what model? Long coding model, and he's like, oh, there's this big layer of was it positive on the inside? Anyway, mixture of positive and negatives, but there wasn't really a correct organization. He just kind of said, it looks like plum pudding. There's spotty kind of positive charges in this negative overall area. And then who came up behind him? Rutherford was him and there was one more, Chadwick, that were near, not Chadwick, Millikan, that were near each other in terms of years. What did Rutherford discover? The nucleus, and he said it was hard, dense core in the middle. It wasn't dispersed like JJ thought it was. It's pretty localized in the middle. And then with reference to like these alpha particles, he shot at it and they kind of bounced off. What did he say he thought was inside the nucleus? Well, it's hard dense core with something in it. Positive charge, which he termed proton, or somebody, Goldstein or somebody did. So once we got there, we were like, okay, we got some structure. It's got a nice little central area, and then there's this area around it, which we're not sure what's in it, but we think it's the other subatomic particle, the electron. What did Millikan do? Well, job experiment. So basically, he piggybacked off JJ. JJ was like, there's an electron. Millikan said, the electron has this mass and this charge. Just elaborate it a little bit more. All right, and then, not quite for yet. Chadwick kind of helped discover the fact there was a neutron kind of playing nice inside of the nucleus, so the protons weren't like repelling each other. And then we come to Bohr. And that Bohr model you have seen like in 7th grade, there were these rings. You know what I'm talking about? Okay, that's kind of what our topic is on today. But before we can really recognize what the Bohr model is, we have to talk about why it matters. And the reason it matters is because we can actually now talk about, what did he say existed on those rings, by the way? Say again? Electrons, right? So there's this electron out here. That electron is like the bane of our existence. Really, it does everything. We have to know so much about the electron because it literally causes everything to be reactive or non-reactive, everything to cause fires or makes water wet. I mean, there's so many things that this electron can do. One thing in particular is actually to create light or to create color. So we talk about all these different wavelengths here, all based on what the electron is doing, which is what we can actually visualize. So all this is caused by electrons, which we're going to talk about in a minute, but let's first talk about what light is. So question 9 talked about a piece of potassium, right? You got a piece of potassium metal, and it said if you shined yellow light, I know this is orange, but it's close as I have. If you shine yellow light on the potassium, it made an electron. These are electrons hanging out in potassium. It made an electron jump out. Versus if you shined red or orange light on it, it wouldn't do that. Okay, so there's something, I've drawn this very specifically. What do you notice is different about my two waves? How do you? It's what? It's wider, so it's longer. Which one looks like it's traveling faster? Let's call it yellow. Okay, so it's yellow. Okay. So this is the red-orange one. Oops, that's not the O, not a Q. Okay, and that's yellow one. Okay, so who's traveling faster, supposedly? Yellow. So who do you think has more energy? Yellow. So why do you think the yellow one can pop an electron out? Because it has more energy. It's traveling at a higher velocity. It hits the potassium. It knocks loose this electron by providing energy to it. The electron pops out. The red one just, it's long, it's slow. Does it have enough energy? No. Okay. So this is called the photoelectric effect, because if I say photo, okay, if I say photo, what does that prefix mean? Light. And what does electric kind of sound like? Electricity. Did you know that electricity is just straight up electrons flowing through wire? That's it. It's just electrons. Something's helping push it like an electromotive force, but electrons are moving. So this means electricity, or electrons. Okay, so the photoelectric effect is how light, these like, for example, these two light wavelengths, how they can interact with matter in such a way to make electrons move. Who cares though, right? What are these electrons doing for us? Powering what? Well, I mean, is this remote powered by light hitting it? No. Can you hold up something that is? What's this little thing right here?
Oh, solar.
Little solar panel, right? Now I know we're not in the sun, but these fluorescent lights do the same thing. If you hid this away in a drawer for like 2 weeks, it would be dead as a doorknob. But what's happening is the light here has energy. It hits inside, and there's some sort of storage device that holds on to that light energy, and it allows electrons to move. So when you push a button, it activates, and it actually, types down what you want it to type. These are all like light powered. There's no batteries in there. Thought that was cool. Okay, solar cells will work this way, so they have to be exposed to light. Otherwise, we use other chemical processes like, I'm not taking this out because there's sulfuric acid all up in here now. This battery's dead. But like a AAA battery or a AA battery, there's sulfuric acid, some lithium, zinc, and other things that have their own electrons, and they just kind of toss them around, which makes electricity. But eventually that's going to die because there's not a renewable source of acid or lithium or zinc or whatever. This is a renewable source of energy because it doesn't go away. At night, yeah, but it's still there. Okay? So that's what the photoelectric effect is. More questions on reading guide 5. That was the big question I knew you guys would have because it's not exactly lined out in the book very well. Can we move on? Yes or no?
Yes.
Yes, okay. So let me show you a video first. And it's always the case, guys. Okay. I like to make sure I'm entertaining myself during my planning period. Okay.
Between us and the universe. Through light, we can experience light is the connection between us and the universe. Through light, we can experience distant stars and look back at the beginning of existence itself. But what is light? In a nutshell, light is the smallest quantity of energy that can be transported. A photon, an elementary particle without a real size that can't be split, only created or destroyed. Light also has a wave-particle duality, being kind of a particle and a wave at the same time, although this is a lie. Also, when we say light, we actually mean visible light, which is a tiny part of the electromagnetic spectrum, energy in the form of electromagnetic radiation. Electromagnetic radiation consists of an enormous range of wavelengths and frequencies. Gamma rays have the smallest wavelengths because they're the highest energy photons, but most gamma rays are just under 10 picometers, which is still way smaller than a hydrogen atom. For reference, a hydrogen atom compared to a cent is about as big as a cent compared to the moon. Visible light is in the middle of the spectrum, in the range of about 400 nanometers to 700 nanometers, about the size of bacteria. On the other end of the spectrum, radio waves can be up to 100 kilometers in diameter, while the biggest wavelengths we know exist can span from 10,000 kilometers to a baffling 100,000 kilometers, way larger than Earth. From a physics standpoint, all these different waves are the same. They all have the wave-particle duality and travel at c, the speed of light, just at different frequencies. So what makes visible light special then? Well, absolutely nothing. We just happen to have evolved eyes that are good at registering exactly this part of the electromagnetic spectrum. This is not a complete coincidence, though. Visible light is the only set of electromagnetic radiation that propagates well in water, which happens to be where most eyes first evolved millions of years ago. That was a smart move because light not only interacts with matter, it's also altered by it and can be used to gather information about the world around us with almost no delay, which is arguably really helpful for survival. Okay, where does light come from? A vast range of electromagnetic waves are created when atoms or molecules drop from a higher state of energy to a lower one. They lose energy and emit it in the form of radiation. At the microscopic level, visible light is created when an electron within an atom, that is, in an excited state, drops to a lower energy state and loses this excess energy. The same way incoming light can elevate an electron to a higher state of energy by being absorbed by it. Macroscopically, the moving charge of the electron creates an oscillating magnet field, which creates an oscillating electron electric field perpendicular to it. These two fields move themselves through space, transferring energy from one place to another, carrying information about its place of creation with it. Why, of all the things in the universe, is light the fastest thing there is? Let's change the question. What is the fastest way to travel through space in the universe? It's c, exactly 299,792,458 meters per second in a vacuum. 1 billion kilometers per hour. Electromagnetic radiation just happens to move this fast. Any particle that has no mass travels at c, without acceleration or any in between. The light that's being released from a candle does not speed up until it reaches light speed. At the very instant of its creation, its speed is c. So why is c, or the speed of light, finite then? Well, nobody knows. Our universe is just built this way. We don't have a smart answer here. So light is a part of a spectrum, an elementary particle that also behaves like a wave, propelled by two perpendicular fields traveling at the speed limit of the universe. Okay, that's nice and all, but what about all the crazy stuff about traveling at the speed of light and time, the twin paradox, quantum stuff, and things like that? We have to save them for another video. For now, let's just be happy that we evolved eyes that pick up waves of information permeating the universe, making us see things that help us to put our existence into perspective.
Okay, so that might be a little above our pay grade, just a teeny bit, but what you should have gotten was light travels at what speed?
3.00 times 10 to the, do you see it on the bottom screen? 8 meters per second, okay? Another thing is that we call light, but what we're saying is we're not actually being so inclusive. We're saying visible light, right? So what are some things that we know, what are some things that are included in visible light? That's actually right outside. What's invisible light, guys? What are some colors? Good, you did, right? Every color that we know about is all visible light, okay? So before I move on to what this is, let's talk to your neighbor first. I want you guys to come up with as many examples of waves that fit into the electromagnetic spectrum. Go. Alright, this is a beautiful back over here. Okay, but this is supposed to be going from what to what? Can you tell what I'm doing? From what? So this could be termed that highest concentration of energy, but do you see how short this is? This is a short wavelength, and then I'm transitioning to a long wavelength. Okay, so first group over here, you come in the 4. Give me any form of energy or wave that you can think of. Gamma ray. Okay, gamma rays are pretty darn short. Okay, so gamma ray is the shortest form of electromagnetic spectrum or electromagnetic waves that we know. Back area? X-rays. That's actually the next one. Okay. I don't know if it's ray. Okay. X-ray. All right. Middle area here. Do you know the form?
Ultraviolet.
Ultraviolet. That is the next. So ultraviolet, also known as UV. How do you guys detect UV waves? Okay, but the sun has lots of energy. It's got visible light as well. We can see the light coming out, like some of the colors coming at us, especially if we see a rainbow. How else can you detect it? Our bodies are wonderful at detecting all kinds of things. Right, so thermal energy is one way, but also if you've ever been sunburned, right? So your body can detect UV rays by feeling heat, and then the effect of that, which would be a sunburn. That's damaging your skin, right? Damaging your DNA, mutating your cells, melanoma in your mid-20s. All right, so gamma rays we would never actually probably be exposed to, because then we would become the Hulk, right? Consequence of gamma rays. But we probably are exposed to them by chance, though, by other forms of radioactive decay. X-rays you're exposed to anytime you go to the dentist or the doctor a lot of times, but we have a way to detect them. It's on a special photographic kind of paper. UV rays. Let's keep going. Sorry, let me just keep going. You guys have one? Say again? Microwaves. Microwaves. All right, remind me to tell you something special about microwaves in a second. Up here? Radio waves are the longest. That's AM and FM. FM is short, AM is long. Okay, right here. Infrared. IR, and that's a form of like, who's ever seen like infrared cameras? You can see heat locations or hot spots. So it's detecting a thermal energy. One more. Say again. Radar is in here. I cannot remember for the life of me where it is, but it's in here. One more. Visible, right? The one that everybody's looking at right now. What color am I writing with on the board? Blue, and that's because light's hitting it, but what's reflecting it back? Blue, not all the other ones are being absorbed, right? So, and I remember this, gonna X your voice in my radio, because in AP Chem we have to memorize the order, so that's how I was thinking about as I was writing it. So, special fact about microwaves. We've all seen a microwave, right? Big fat liars, you've never seen a microwave. You've seen a microwave machine. But you've never seen a microwave because you would have died. Okay? So here's your microwave, right? Little start button, little screen. Okay, there's some ramen in there. Okay, so here we go. What's on the front of the screen? I mean, what's on the front of the microwave? A protective screen, right? So it looks like kind of like this. You can still see through the screen because, like, how else would you know if your ramen's boiling over or not, right? So you can see through it. So I'm gonna come right back to this. I'm off on my tangent already. So here's microwaves. Radar's right here. Infrared. Okay. Micro is like here-ish. Wow, that's really off. You guys see how off that is? I'm over here. Okay. Anyway, micro is like 10 to the negative third. How many? What is that in meters? 10 to the negative third. 0.0001 meter, which is in terms of a better unit. How would I express that? Not centi. 1 millimeter. Okay. Hold up a millimeter for me. That. Okay. How big do you think those little holes are on the screen of your microwave? Say again? If they were 3 millimeters, we would all be dead. Let me tell you why. So these are big because I'm drawing them for you to see from the board. But does anybody know how a microwave, the actual wave, works? Charles?
There's something inside of it that kind of makes the microwave. This microwave basically produce massive amounts.
So you're close. There's something that I'm going to fill the gap there, okay? So the microwave hits your food. Your food usually has some sort of moisture in it, like chicken breast will have moisture in it, or ramen, there's liquid surrounding it. The water is pretty much the only thing affected by the microwave itself. So the microwave hits the water molecule's chilling, it starts to speed up because it's getting hotter, it speeds up, it's getting hotter, it speeds up, it's getting hotter, it starts to boil, ding, the microwave's done. Okay, so what's happening is the microwave's targeting the water molecules in the food. Now, if the screen wasn't there, the microwaves would go straight through the plastic or the glass. And where would it come? What are you guys made of? What's your body water? How much? I think it's 65 to 75% water based on how well you're hydrated. So, what would happen to your body? You'd be chilling and you feel kind of hot. It's hot here. And then you would boil to death. You would boil to death if the screen was not there. Right? So, those little holes. Okay. No, that's a safety feature. They don't let you that. So, if the microwave is approximately 1 millimeter, how big do you think those holes are? How big?
Central,
Yes.
could I please have a deep also for dismissal?
Got it. I'll figure it out.
Thank you.
All right, so that's my fun fact about microwaves. But they do have a microwave at UNC Charlotte that's not contained. It's not in like the box. It's because they do research with it. It's a ray. So this microwave that you can't see is going here, and there's a big screen that says, "Do not put your hands here when on." And someone did, and I think they like vaporized their finger or something. Oh. Fun fact of the day. Okay, pull out these notes. Okay, question. Yeah. It does refract. It does refract very, very well, and you can't. It's not visible. Not very visible. That's really why. All right. So have you found this in the back of the stuff we were taking notes on Friday? Yes. I got one person saying yes. The rest of us, okay, cool. So there's your quick definitions. Just because I'm going to be mentioning words a lot, I want to make sure you're clear what the terms mean. And then we're going to do some calculations, and then we're going to color, and then we're going to do calculations. All kinds of things today. I'm videoing. Watch me on YouTube. Oh, hold on, grab that worksheet before you leave. It's on the lab station. So do you ever hear me say the EMS? It's not like an emergency system. EMS, electromagnetic spectrum. Very good. And so that includes everything that's here on the board and everything we've talked about. The electromagnetic spectrum always is going to be, you're going to talk about the waves in two ways. Wavelength. So what would be a good unit for wavelength? Length. Meters, right? Many times this wavelength will be in meters, but we're talking about really, really teeny tiny things. So what would be a smaller unit per meter? Nanometer is probably our more common version of that. So that is going to be our unit for wavelength. Now this upside down Y thing is called lambda. It's the Greek symbol for lambda. Lambda. Actually, I don't know what the Greek symbol is regarding, but this is what we'll be using in our equation. Frequency is the other variable that we'll speak of about our waves, and it basically just means how fast you pass a point. So if I'm standing here and you pass me 3 times in a minute, are you moving fast? No, but if you pass me 3 times in a nanosecond, you're moving pretty fast. So that's just our frequency, which makes sense. That's going to be distinguished by the variable v, or a v with a little like hat on it. And the units, you'll notice it's not seconds, it's not time. It's per second. 1 over second is different than seconds. Or seconds to -1. Or HERTZ, hertz. Which, can you imagine that this was a scientist? Yes, yes, this is a scientist, and guess what? He had named a unit after himself. So the unit is hertz.
Lastly is amplitude. We will not be like really calculating with amplitude though.
It just simply gives us an indication of like how intense the wave is. So if it's like a dark burgundy red or if it's a pinky red, that would give us intensity of color differences. But this is your friend. This is the speed of light equation. So the speed of light is, again, 3.00 times 10 to the 8th meters per second. So you will accidentally memorize this probably within 2 days because you'll use it a lot, okay? So the meters per second, does that correlate with what we just talked about up here? Yes or no? Yes. Yes, and that has to, because these units should be looking at each other, making sure they cancel or making sure they kind of collaborate. So C, which is in meters per second, is equal to, what should wavelength probably be recorded as? To match this, though, now a lot of times you're right, it will be in nano, but to match this, it should be recorded as meters, okay? And then what will V have to be recorded as in units? Not just seconds. Per second. So 1 over seconds is what he's saying. So 1 over seconds comes together to make meters per second. Meters per second. So they all come together to make their equation work. Okay? All right, so now we're going to calculate with one of these. So we're going to start with violet light. Oh, I didn't say that over here. Where do you think, knowing this is our range of waves here, do you think visible on the visible spectrum, violet light falls towards UV or IR? UV. Why UV? Because UV is, what's the correct terminology for this? Ultraviolet. What's IR stand for? Infrared. Okay, so that's your spectrum. Roy G. Biv goes this way. R, Roy G. Biv, B, or V, or violet. So we're going to talk about who's longer. Who's the longer color? Red. That's a really long wavelength. Violet, on the other hand, little bitty wavelength, apparently according to how our spectrum is aligned. So that's one thing we'll talk about more today. Okay.
So here's our question.
What is the frequency of a violet wavelength that has a wavelength of 400 nanometers? All right, so give me the equation, the only one we've learned. C
equals
lambda times, I'm going to use V for frequency. It is kind of like velocity, but we're talking frequency here. Okay, of these 1, 2, 3 variables, which is our question? The V, the velocity or frequency. And then what do we already know? We know the wavelength and we know the speed of light. It's not up here, but it's on your paper, right? So we know everything except for V. That makes sense. This is just an algebraic equation. You're just going to rearrange this baby and solve. But we have to make sure units match. So give me C again. Units? Meters per second. So what is wavelength in this case? 400 what? Nanometers. Uh-oh, what do I already see? Mixed units, right? Meters and nanometers, they're close, but they're not the same. So I'm going to have to use dimensional analysis to convert this nanometer to a meter, or to a version of meter, so that the units can match together. So here we go. This is what we just did last unit. 400 nanometers. Okay, think to yourself on how King Henry died, count, and think about what's going to be your single conversion right here. Write it out if you can't think it, because it's not, it takes you about 2 seconds to write down. All right, Bennett, what's going to go on my top of my fraction? Just give me the unit, not the number yet. The meter. Okay, everybody, what's on the bottom? Nanometer. Who's the bigger unit? Meter, so it gets the 1. Okay, how many nanometers are in a meter? Don't tell me big numbers, tell me exponents. 10 to the... Think about this. King Henry died by. Okay, we're at by. That's meter, right? Drinking, chocolate, milk, dot, micro, dot, nano, nano 9, you can't mess it up. Okay, so it's 10 to the 9th. I mean, you don't have to write it out all the time, but if you can think it, you gotta think straight. So I just need some space because my marker is a little bit on the goofy side today. I'm just gonna fix this later. 10 to the 9th nanometers in 1 meter. So a billion nanometers in a meter. All right, convert that, and then tell me that in scientific notation, please. 4 times 10 to the -7th meters it is. Okay, now we have wavelength, woohoo, in a reasonable way. So this is 4.7, I don't know where I get 7 from, 4.0 times 10 to the -7th meters. And then again, our question is still frequency. Okay, so we have everything we need to plug into the equation. Before we start plugging in, I usually have people rearrange the equation first, just so we're all on the same page. How do I get V by itself? Divide by what? Lambda, wavelength, whatever you want to say, okay? So that you have to do it on both sides, just basic math. When you divide by lambda on this side, it cancels out, and then we end up with having C over lambda is equal to V. So this is the happy equation that we will be plugging everything into, right? So what is C? 3.00 times 10 to the meters per second. Good. Divided by 4 times 10 to the -7th meters. Before you calculate, your calculator is not as smart as you think it is, and so user error usually occurs here. You must put parentheses around your numerator, and when you divide, parentheses around your denominator. Calculate. And I'm telling you to do this now because some people make stupid calculator errors on their tests because they didn't like the parentheses or put exponents exactly. Which I can't help that. Gotta make sure your fingers work. Alright, so I'll start at 7 times 10 to the 14th. What are the units? Everybody, what unit cancels? Right, there's a meter on the top and there's a meter on bottom. So meter and meter cancels. What's left? Say again? Per second, not seconds, slash second. So it does mean we write this as either slash second or seconds to the -1 or hertz. I don't ever really write hertz though because it doesn't help me see the connection between what I was just doing. So is that a high frequency or a low frequency? I mean 10 to the 14th, heck yeah, right? That thing is moving, it is booking it. So this violet light is moving pretty dang fast. Do you think this frequency would be higher or lower for red? So think, hold on, let's go back to here. Is this short or long wavelength compared to this one? Violet, is it short or long? Shorter. Do short wavelengths? Let me demonstrate. Here's a long wavelength. Okay, pretty slow. Low energy. Okay, so what was that? Fast, high energy, and a what kind of wavelength? Short wavelength. Okay, so do you think, so this is violet, right? It's a short wavelength. Would red be a higher frequency or a lower frequency? Lower. It's one of these slow ones. Okay, so it's going to not move very fast. So sometimes you can actually make sense of your answers if you compare something. All right, let me pause on this one. I'm giving you another one, okay? What is the wavelength of red light with a frequency of 1.2 times 10 to the negative, 10 to the positive. Oh gosh, guys. I'll fix this marker while you guys are working. (1.2 times 10 to the 14th hertz. What is the wavelength of red light with a frequency of 1.2 times 10 to the 14th hertz? Go. I need to see you practicing with the equation and the calculator. Get down the data you need because I'm about to fix this marker. Remember, how can you interpret hertz? No, just per second. It's just a normal frequency. Per second it is. Check your answer with a friend next door, please. Your calculator is not winning. You are in terms of putting it in. All right, Bennett, can you get me started? Numbers?
Yes, 2.5 times 10.
2 point what?
5 times 10.
Nope. Calculator. 8 and a 14. Double check that. Can I get, Alicia, what you got? Good. So I can usually tell when you forget parentheses or you accidentally put a negative or something you didn't mean to, because you're acting, I mean, you guys can do this. When exponents are divided, what are you supposed to do with them? Subtract. 8 minus 14 is -6, right? So you already know you should have a negative exponent because this is a bigger number. Number logic, and then assess your answer. So what are the units here? So hold on, what are we solving for? What unit? I mean, what variable? Wave length? Length, okay, so what unit should this be? Meters, right? And then you double check. Per seconds cancel. The only unit left is meter. Okay, so this is wavelength. Is that longer or shorter than the violet? Violet was what? 4.0 times 10 to the -7? So technically that's shorter. It's not actually red, that's because I just made that a question up. Okay, so do me a favor. Let's grab just a couple of colored pencils and this worksheet from back here. Let's go. And then we're just going to take a pencil break and then we're going to go back and okay. So you will need a couple of colored pencils. You can start the person next to you. Or we can start. I know. You're fine. You're good. Take the monkey. All right, do 1 through 6. When you get back to your desk, 1 through 6. If your buddy is not here, you need to grab a sheet for them and write their name on it. Okay, good. Grab one for 30. Take one for that paper. Same whoever. So you can grab an extra paper for Simon, and then who's Audie's buddy? Yeah, I got Ben about that. Vishal, are you Audie's buddy? Oh no, he actually grabbed a worksheet. I had to call him grab him. And then I got Dennis, got it. Sorry. Alright, try to do 1 through 6. More focus on the questions that you may color just for a little therapeutic relaxation from you. They're right in front of the work in front of the college. Alright, so you guys just have a couple minutes to do 1 through 6, and then we're going to talk a little bit more about atomic structure, and then go back to finishing this. Alright, so I know you can do 1 and 2. Prisms are also known as diffraction gratings. So who's ever seen the Pink Floyd t-shirt? Prism and then rainbow on the other side. That's exactly what you're drawing. Liam, can you tell me why do you think their labeling is plural, like reds versus red? Right, there's dark red and there's light red. There's different shades of red. It's not just red. There's not only 7 colors in the world. Alyssa, what do you think about the traveling, the speed at which they travel?
Yeah, they're all the same.
All the same. What's that speed?
3.00 times 10 to the 8th meters per second, the speed of light. All light travels at that speed. It's just some of them have different wavelengths that they are traveling at. Do all the colors of light have the same energy? What you think, Dean?
No.
No. Who's got the most energy?
Violet.
Violet, who has the least energy?
Right.
Good. Everybody tell me who's the longest type, or which color has the longest wavelength? Red. And who has the shortest wavelength? Very good. Okay, this last part 6. Talk to the person next to you to establish a sentence that would show the relationship between energy and wavelength. You've got about 20 seconds to finish that, and then we're going to go back to notes. We only got 36 for now. You'll get that in a second.
Yeah, they do.
All right, so I would say something like longer wavelengths longer wavelengths have lower energy, smaller or shorter wavelengths have higher energy. So is that a direct or an indirect relationship? All right, let me remind you guys, if you're talking, you gotta come back to me now, okay? So a direct relationship is that if something goes up, the other variable goes up. That means direct. Indirect, when one variable goes up, the other variable goes down. So what's the relationship for energy and wavelength? Indirect. As one goes up, as the wavelength gets long, the energy gets big or little? Small, right? So increasing the wavelength decreases the energy. It's an inverse or indirect relationship. Alrighty, so here's where we are. Does this look familiar? You have some of these on your scientist notes if you wish to pull those out for yourself. I'm just going to give you the basics of Bohr and then talk about why this matters with reference to light. So the Bohr model, so we went through the scientist, and so Bohr was like, I have the answer. Here's where the electrons are. They live in these little rings around the nucleus. And what did he call those rings around the nucleus? Say again? Energy levels, right? So energy levels, also known as orbits. So the orbits term hangs around, but we actually don't call them orbits anymore. They're orbitals. Big change. But orbitals is a new word, okay? But regardless, Bohr was like, there are 4 orbits or energy levels around the nucleus. They are quantized, meaning they have a set amount of energy. And so the ones on the inside, like the first energy level, we call that n equals 1. Okay? And then so forth. As we go out here to n equals 4. N just means energy level. So I'm expecting that you know that. N just means energy level. So who has the most energy? N equals 1 or N equals 4? N equals 4 has the most energy. Think of it like this. Who's in the middle of the atom? The nucleus. Okay, so we're going to call that mama nucleus. Mama nucleus is in here. When you're close to mama nucleus, you're well behaved. Yes, ma'am, no, ma'am. Nothing, no shenanigans. You are low energy. You are very, very well behaved. As you go out, leave the house a little bit crazier, get farther away from mama, maybe not behaving as well as you should be, shenanigans begin. So you have higher energy. That's basically what the atom represents as well. So what he said was that electrons can transition between these energy levels, 1, 2, 3, and 4. So if an electron starts at n equals 2, and it transitions to n equals 4, it's going from a low energy state to a high energy state. Do you think that required energy or released energy? So if I'm jumping, is that requiring energy or am I releasing energy? Loud and proud, people. If I'm jumping, I have some air time here. I'm requiring energy. So energy goes in. And as that electron hangs here, let's say, analogy, you're on a sugar high. You've just got so much energy, you're a sugar high, caffeine high. Can you stay there forever? No, we wish we could, but we can't. Eventually we crash. And as we crash, we go from n equals 4, sugar high, right, down to the ground state, or down to where we were. So when you crash, are you releasing energy or absorbing energy? Releasing energy. So energy out. So there's a system. You can make an electron become excited and come out to an outer energy level, and then you can have to allow it to go back down to its stable state, go back down to ground state as it falls back down. One requires energy, one releases energy. So that's what Bohr thought. And it's generally true still, except the atom doesn't exactly look like that from our theory now. We found this to only be true for hydrogen. That's it. Out of 110 or so, only true for hydrogen, this structure. But what is still true is that when these electrons move, and I didn't mention this, when these electrons move, and they go from an outside energy level in, didn't mean to do that, so they go from outside energy level in, they release light. And if it's a visible light, we can see it. So look at this one. We're going from like n equals 5 to n equals 2. Is that releasing energy or absorbing energy? Releasing. What color energy? What color? Violet. That's a lot of energy, right? High energy wave, it's violet. And then if you go from n equals 3 n to n equals 2, how much energy do you think that lost? A lot or little? A little, so what wavelength does that correlate with? Red, because red doesn't have much energy. So we can actually see this. This is called a spectrum. So let me show you what that spectrum looks like. Okay, so it looks like this. If it releases low energy light, it's red. If it releases high energy light, it's either blue or purple. And we get this little like fingerprint, because hydrogen's looks very different than boron's, very different than nitrogen and fluorine and helium. So because this emission line spectrum is different for every single atom, we call it an atomic fingerprint. Why does that make sense? Like, do you have the same fingerprints as somebody else? Supposedly not, right? That's why they use it in the legal system forever, because they try to look at fingerprints for some individuality. Well, the atoms don't have fingers, but they have this method of us exciting them, and then they release light, and we look at them and go, this particular pattern looks like that of nitrogen, aka the atomic fingerprint. Another name for this is the bright line spectrum. Can you figure out why they call it that? What are these? A bunch of bright lines. Okay, and so we will actually do a lab with this tomorrow, most likely, which will let us actually see these bright line spectrum for different atoms, different elements. But Bohr's model is based on us being able to explain these bright line spectra. Okay, so you're trying to make some associations. Bohr model, light drop, or electrons drop, light's produced, makes pretty picture. Got it? Okay. So I'll come right back to this. No, yeah. Okay, so this is what we've been saying. Write down what you need to, that first sentence up there. That's what I keep saying, but now you can write it, which might help streamline your thoughts some. I give you very skeleton notes sometimes. Just because I don't have it on your paper does not mean it's not important. So if I'm leaving it on the board, it's probably there for you. So as these electrons go from an outside energy level to an inside energy level, they're releasing photons. What is photon again? Light, so bundles of light or bundles of energy. And we actually take advantage of this in everyday life because we use neon signs. We use stoplights. We use all kinds of things that require us to excite some electrons. As they fall or as they come down to this thing called ground state, they release visible light, which we have to see to do stuff with. So that's your definition of photon, which was on your reading guide. So that's not the most important thing here. But this is an image that's supposed to indicate a little bit more about what's happening. You should know how atoms become excited. Okay? So you can excite elements inside of an electron in 3 ways. 1, you can heat them up. So how would we do that in the lab? Boil water. Come on, give me more. Bunsen burners, right? So we will do this not tomorrow, but maybe this week. We'll light them on fire, heat them up. We'll throw some electricity through them. So I'm the electrocutioner, so I will do that for you, and you guys will see the results. And then a third method is to use high energy light. So basically you can use light, like violet light or UV light, which is really high energy, to excite electrons. So as they become excited, they start at this state, which is called ground state. Ground state just means you're stable. You're grounded. Not like you're grounded at home, but like you're stable, you're chilling, and you're happy. It's a stable place. But once you shine some high energy light or fire or electricity on this electron, do you see it bounces out to an outside energy level? It goes from like this ring to the outer ring. Okay, this is now termed the what state? Excited state. Can it stay in that excited state forever? No. So this absorbed energy, which you can't see absorbing energy, but what you can see is the result of it falling back down from excited. So once it's here, I'm going to draw it up here so it's easier to see. Once it's here, it's going to have to fall. And as it falls, what do you get to see? Light. Okay, so as this falls, light is released. And then hopefully it's in such a way that we can see, which is like a color. And that is the premise of the Bohr model. That is what we use it for most commonly, is relationships between energy and light. Because it's really not useful anywhere else. Okay? So that's kind of our energy relationships with electron or energy levels. All right, take a minute if you're still working there. Go back to your worksheet. And you need about 10 minutes to get through question 18. Work with the person next to you. So basically finish the page for me. I can go back. Now that little diagram's a little hard to see, so I'm going to pull that up so you guys can see it better. So here's the question you're on right now, right? Yes? Okay, so that first line over here, the red part of the bright line emission spectrum is 656 nanometers. If you need to add that to your sheet. The second line, the blue-green line, is 486 nanometers. The blue-violet line is 434 nanometers. And the violet is 410 nanometers. And this is all the bright line spectrum from hydrogen gas. That's really the only part you need in that image. All right, finish the question you were on, and then let's review pieces of this before you head out today. So I'm going to start on question 12. So the other ones I think you guys could achieve very easily. So here we go. I'm going to call out and get some help here. Then do boron and hydrogen emit the same wavelengths of light? Say again? No. Okay. In terms of what that looks like here, I got 13. The spectral lines for atoms are like fingerprints for humans. How does this compare? Basically, every element shows a different emission spectrum. So you can identify it based on its emission spectrum. Not like you'd know by memorization, but you would know it that they were different based on their emission spectrum being different. 14, you fill in the blank as I go, okay? Electrons and protons, loud and proud, attract each other, right? Positive and negative. That's how it works in chemistry. I know it's 21st century, but that's how it works in chemistry. As an electron gets closer to the nucleus, the attraction to the nucleus gets stronger, right? Remember, positives and negatives attract, so as the electron gets closer, it's more attracted to its nucleus, which makes it stable, aka at ground state. For an electron to move from an energy level close to the nucleus to an energy level far from the nucleus, it would need to gain energy because you've got to jump and get up there. And then 17, lose energy because it's falling from excited to ground. Down on 18, this arrow is going from n equals 2 to n equals 5, so is it gaining or absorbing? I'm sorry, absorbing or releasing? Absorbing. Absorbing is the better word for that, right? And that's because it's going from like a ground state to an excited state. Ground state to excited state means you absorb energy. Can you see that absorption, guys? With your eyeballs? No, but if it went releasing energy, potentially could you see it? Yes, because hopefully if it's in visible spectrum, you could see it. All right, so these 4 pictures correlate to the Bohr diagram in Model 2. So we had 4 colors to work with, right? Red, purple, blue-green, and blue-violet, right? What should this little teeny tiny short wavelength one represent? Violet, and does it have the most energy or the least energy associated with it? So, sorry, does it have the most energy or the least energy associated with it? Look here, and here, and here, and here. The most, right? Violet has the most energy. We've said that like 5 times just today. And then going down here to D, this wavelength is relatively long, and it has the least energy, so this is the red one, which is what? N equals 3 to N equals 2. Okay, so I think we checked off 2 things, and if you already looked over here, I modified. There's a Ed Puzzle video that's up. It's on light calculations, which we have one more variation of calculations tomorrow. Feel free to watch it. I'm making it optional now because I already done half of it, but it's like a 5-minute video. So that's review. Pogl, check that Pogl, P-O-G-L things that you just did now. And then finish PS4, okay? So let me pull up PS4, and then you guys have a couple minutes to work on that. You may put your laptops up though, okay? You just did it. I said laptops up, I meant it, but you don't have laptops, so.
What do you mean
Calculators it is. No, well, unless you need it for problem set 4. Problem set 4, right here. I'm going to ask for you to cap your problem set out because I'm going to actually help you with part of this. Ready? Problem set 4 out. Can you thumbs up? Please write down problem set 4. Weak mode, thank you. Alright, then you help me out, Mason. Everybody should have a periodic table close by. Find selenium, Se, selenium. Which group is it?
Oxygen.
It's an oxygen group, so I'm going to call that group 6A, basically, from now on, right? So, selenium, S2 minus 8134. You have to list out the protons, electrons, and neutrons. Mason, get me started.
Protons, 34.
Okay? Alright, hold up. So, everybody tell me how I would approach electrons from here. First off, think to yourself, did it gain or lose electrons?
Gain.
Gain how many?
2.
How do you know?
Because it's negative.
Two more negative charges, right? So how many electrons total?
36.
36 electrons, and then how would you do neutrons?
That's this.
Sorry, mass minus atomic number. I'm just going to put proton to keep that short, and that's going to equal neutrons. So you're doing 81 minus 34 equals 40 what, 7? Okay, there you go. All right, so I got you started. If you've not finished this, I'm leaving this here for a minute, and I'm going to try to take some questions where I need to. But write down what you need to, because you got concept on your homework. So I just FYI, I don't pick anything with just answers, because I legitimately already gave you the answers. Do not pack up yet. I just asked you to work on this for a minute. We're next to you. You're still 3 minutes left in class. I give you the answers on the bottom. You have to show your work. If not, I can't give you any credit or help.
Good afternoon, Chartreuse. A quick bus announcement. Students, if you ride bus 55, you will be on spare bus 146. Thank you and have a good afternoon.
I have to pass you out a letter about vaping and how bad it is for you. I mean, I'm serious. There's been 13 cases of vaping with impurities across the county in like a month. So, and they've had to go to the hospital. One from Proxima last week. So, bring this to your parents and they're going to talk to you about how dangerous it is to do drugs. Okay? Bring this to your parents. I got this. I'm not sure if you have staple it to their little absentee form and put it in the absence box. Then staple Cody's little thing, Cobble, and put it in the absence box. Same thing. You staple it on the little thing, worksheet, and put it in the absence box. All right, you may pack up now if you need to. Calculators away, etc., etc. Do not